All right, welcome back to the Deep Dive. You're here because you want to stay right on the cutting edge of AI research. And today, we've got a really interesting paper. It's kind of shaking things up in generative models. We're diving deep into PixelFlow. It's a new framework for generating images, but directly in raw pixel space.
Exactly. And that's pretty significant because, for anyone following the field closely, Latent diffusion models, LDMs, have really been dominant.
Right.
PixelFlow offers this compelling alternative, generating images pixel by pixel, end to end. And crucially, it doesn't need a separate VAE or those extra upsampling stages at the end.
Okay, so for everyone catching the short version, let's nail down the key takeaways real quick. First, PixelFlow gives us an image generation model trained entirely in raw pixel space.
Yeah, no pre-trained VAE needed. That's big.
And it gets efficient compute using this clever cascaded flow modeling idea, going from low res to high res.
Right. And the results look good, competitive image quality on ImageNet, and really appealing text-to-image results too.
Okay, great summary. Now, for the full picture, let's really dig into the architecture, the training, the performance, all of it.
Sounds good. So to really get why PixelFlow is a big deal, maybe we should quickly recap the current scene. As you said, LDMs are everywhere, right?
So the images, video, audio, even 3D stuff, they're kind of the go-to.
Exactly. And they usually work in those two stages the paper mentions. You've got a pre-trained VAE, the Variational Autoencoder.
Which compresses the image, right, down into a smaller latent space.
Precisely. Takes that high-dimensional pixel data, squeezes it down, then the diffusion model works its magic in that compressed space. It was a smart way to handle high-res data without, completely breaking the bank computationally.
So the VAE is like a smart zip file for the image, lets the diffusion model work faster, and then it unzips it at the end.
That's a pretty good way to put it, yeah. Reduces complexity, keeps the important stuff, ideally. But, and this is key, the VAE and the diffusion model, they're usually trained separately.
Ah, okay, so they're not optimized together.
Exactly. That decoupling can sometimes limit the overall performance, makes it harder to fine-tune the whole system perfectly end-to-end.
Right, so if you didn't want to use an LDM before PixelFlow, what were the other main paths?
Well, the most direct alternative is just doing diffusion right in the pixel space. Raw RGB values, no compression.
Okay.
And early diffusion models did try this, but as the paper highlights, the computational cost just goes through the roof, especially for high-resolution images.
Yeah, I can imagine. Tracking every single pixel relationship must be massive.
Astronomical, yeah. So to try and deal with that cost in pixel space, people often use a cascaded approach.
Cascaded, how does that work?
The idea, like the paper shows, was to generate a low-res image first using a pixel-based diffusion model,
Okay.
and then use a series of separate upsampler networks to progressively increase the resolution and add detail. The output from one stage feeds into the next.
So like building it up, start blurry, get sharper and sharper with each step.
Exactly. Models like cascaded diffusion models, CDMs, did this. It helped with the compute compared to one giant pixel model, sure.
But, sounds like there's a but.
Well, yeah, you're still training and managing multiple different networks, the initial generator, then all those upsamplers.
Right, so still not truly end-to-end optimization.
Precisely. The components are still somewhat independent, limits the synergy you might get otherwise.
Okay, so that sets the stage perfectly.
Yeah.
How does PixelFlow actually get around these issues?
PixelFlow, and you can see this in their diagram, figure 1C, it's a one-stage end-to-end solution.
Home stage, right.
It works directly in pixel space, but, and this is the clever bit, it achieves efficiency without needing a VAE or separate upsamplers. The key is using a unified set of model parameters to handle multi-scale samples across those cascading resolutions. And the technique enabling this is called flow matching.
Unified parameters for different resolutions.
Okay.
That sounds pretty elegant. How does flow matching make that possible?
Well, the basic idea for efficiency in PixelFlow is this progressive denoising strategy. It starts generating at lower resolutions, where the noise levels are kept intentionally high. Then, as it denoises, it gradually increases the sample resolution stage by stage.
Ah, so the really heavy full resolution work only happens towards the end.
Exactly. That saves a ton of computation compared to working at full resolution the whole time.
Makes sense. Focus the effort on the fine details later on.
Right. So during training, what PixelFlow does is it constructs these cross-scale samples, takes a training image, resizes it down multiple times, adds noise to each version at different time steps.
Okay.
Then the model learns to predict the velocity. Think of it as the direction to push a noisy, lower-res image towards a cleaner, higher-res version. It actually takes an interpolation between two adjacent noisy scales as input.
An interpolation, interesting.
Yeah. And the really cool part is the whole thing is trained end to end. You just sample training examples uniformly from all these different resolution stages.
And then for inference, actually making a new image, how does that work?
Inference kind of mirrors the training. You start with pure Gaussian noise, but at the lowest resolution.
Right.
And then the model iteratively denoises and upscales, step by step, through the resolutions until you hit the final high-res target image.
You've mentioned flow matching a few times now. It sounds pretty central. Can you break that down a bit more for us? What exactly is flow matching?
Absolutely. So flow matching, it's a type of probabilistic generative model. The goal is to learn a continuous transformation, a smooth path, basically, that maps a simple distribution, usually just standard Gaussian noise, to the complex distribution of your target data, like real images.
How does it define that path?
It defines what's called a forward process using linear paths. Straight lines, essentially connecting a noise sample directly to a target data sample. Equation 1 in the paper shows this. X equals t times by 1 plus 1 minus t times 0.
Let's break that down. A flow goal is noise, by 1 is the real image.
Exactly, and it is just a time variable going from 0 to 1. So as sat goes from 0 to 1, x moves along that straight line from the noise 0, 0 to the clean image by 1.
Okay, so a direct line from noise to image.
Pretty much. And the model's job during training is to learn the velocity along these paths as vt equals d xt dt. Basically, how fast and in what direction to move at any point along the path.
And it learns this velocity how?
Using a standard mean squared error loss, equation 5 in the paper shows the formula. It tries to make the model's predicted velocity match the true velocity of that linear path.
Got it.
A really neat thing about flow matching, though, is it's not strictly tied to Gaussian noise. In theory, it can learn to interpolate between any two distributions.
Oh, interesting. So like image to image translation.
Potentially, yeah, or style transfer. That flexibility is definitely one of its strengths.
Super interesting. Okay, now let's connect that back specifically to how PixelFlow uses it for the multi-scale generation.
Right, so PixelFlow generates images by stepping up the resolution, like we said. To set this up, it takes the target high-res image and recursively downsamples it by a factor of 2 each time.
Creating like a pyramid of lower res versions.
Exactly, like figure 2 in the paper shows.
Huh.
The whole process is split into S stages, index 0 to S minus 1. Each stage works over a specific time interval defined by a start state, xt0, and an end state, xts1.
Yeah.
And it's worth noting, if you just had one stage, S equals 1, PixelFlow basically just becomes standard flow matching on the full image.
Right, makes sense. So how are those start and end states defined for each stage in the multi-scale setup?
Equations 2 and 3 in the paper lay it out. For the start state of stage S, you take the target image by 1, downsample it by 2 to the power of S plus 1, then upsample it back to the stage's size, and add noise based on the start time 0.
Okay, bit involved. And the end state.
For the end state XTS1 of that same stages, you just downsample the target image by 2 to the power S and add noise based on the stage's end time TS1.
Gotcha. And they mentioned specific interpolation methods.
Yeah, they use bilinear for downsampling, the down function, and nearest neighbor for upsampling the up function, unless they say otherwise.
So let me see if I have this right. Each stage starts with a kind of blurry, noisy version of the target and aims to get to a slightly sharper, less noisy version.
That's the essence of it, yeah. And to train the model, they sample intermediate points by just doing a linear interpolation between that start and end state for the stage. Equation 4 shows this.
Okay, and there's like a rescaled time within that state.
Exactly. This is 2 minus t0 divided by ts1 minus ts0. The model then learns the velocity needed to move from that intermediate point towards the end state of that stage using the flow matching loss.
And it does this across all the stages, climbing up the resolution ladder.
Precisely. Gradually increasing resolution and decreasing noise.
Okay, let's switch gears to the model architecture itself. You said it's transformer-based, like DIT.
Yes, they use a transformer for the velocity prediction model. Specifically, they build on the diffusion transformer, DIT, and consistently use the XL scale version for their experiments.
It makes sense. Transformers are good at this stuff.
Right. But they made some key tweaks to the standard DIT architecture to make it work well for PixelFlow's multi-scale approach.
Oh, like what?
Well, one big change is in the first layer, the patchify layer. Like in Vision Transformers, VIT, it turns the 2D image input into a sequence of 1D tokens.
Okay.
But unlike latent transformers that work on VAE outputs, PixelFlow's patchify layer works directly on the raw pixels.
Ah, direct pixel input. How does it handle the different resolutions in a batch efficiently?
They use something called sequence packing. Basically, they take the flattened token sequences from different resolution images in a batch and just concatenate them together along the sequence dimension.
Clever. So you can run attention over different sized inputs efficiently.
Yeah, exactly. Another change is they swapped out the standard sinusoidal position encoding for rope rotary position embedding. Well, Ropey has shown it's better at handling varying sequence lengths, which is obviously important here with the different resolutions. They use a 2D version, applying 1B Ropey independently to height and width dimensions.
Okay. Seem to work better than the old Synco's embeddings for their setup.
Apparently so, yes.
And how does the model actually know what resolution it's currently looking at?
Good question. They added a specific resolution embedding. It's a sinusoidal embedding calculated from the absolute resolution after the patch embedding step.
And that gets added in.
It gets added to the regular time step embedding before going into the transformer block, so the model gets explicit info about the current spatial size.
Makes sense. And finally, for text to image, how do they adapt it?
For text to image, they added cross-attention layers. These come after each self-attention layer in every transformer block.
So the text prompt influences things at each step.
Right. It lets the model incorporate that textual conditioning throughout the generation. And for the text embeddings themselves, they used FLAN T5XL, which is a pretty standard and powerful choice these days.
Right, instead of just class conditioning like in the ImageNet case.
Exactly. Class conditioning often uses adaptive layer norm, but for text, cross-attention is more common now.
Okay, that gives us a really solid picture of the architecture. Now let's talk training and inference efficiency again.
So yeah, as we mentioned, training efficiency comes from uniformly sampling examples from all the resolution stages. And that sequence testing helps batch these scale variant examples together, speeding things up and helping it scale.
And inference, how's the efficiency there?
Well, inference starts with noise at low res and steps up, like we said. Within each stage, they use standard flow model samplers. They tried the simple Euler discrete sampler.
Right.
And also the more complex adaptive Doppers 5 solver. There's usually a trade-off there between speed and quality.
Right, typical sampler choice.
And to make sure the jumps between resolution stages look smooth, they also use a renoising strategy. Helps avoid weird artifacts.
Okay, makes sense. Now, moment of truth, the results. Let's start with Class-Conditional on ImageNet, big benchmark.
Yeah, definitely. They tested PixelFlow on ImageNet 1K, generating 256 by 256 images. Used Atom W Optimizer, fixed learning rate. The main metric was FID for shed inception distance.
Standard metric for image quality and diversity.
Right, but they also reported inception score, SFID, precision, and recall for a fuller picture.
And what did they find? Any key knobs they tuned?
One really interesting thing was the kickoff sequence length, basically, the starting resolution for generation. Table 1 in the paper shows this.
Ah, so starting at different resolutions affected the final scores.
Yeah, there were definite trade-offs across the metrics. They had to pick a kickoff resolution that gave a good balance overall.
And what about patch size in the transformer? Did that matter much?
Oh yeah, big time. Table 2 shows this. They tested different patch sizes for generating 64 by 64 and 256 by 256 images.
Yeah.
Well, a tiny 2 by 2 patch at 2 by 256 resolution was computationally brutal, really slowed down training.
Okay.
But going too large, like 8 by 8, made the image quality drop noticeably, even with more training.
So there's a sweet spot.
Seems like it. They settled on 4 by 4 as the default. It was the best compromise between quality and compute cost. And Figure 4 shows some examples. They look really good, lots of detail across different classes.
Okay, so how did the actual numbers stack up against other top models?
Table 4 has the comparison. PixelFlow hit an FID of 1.98 on 256 by 256 ImageNet.
1.98. How good is that?
That's really competitive. It actually beats several well-known latent diffusion models like LDM, DIT, and SIT on FID.
Wow, okay. Better FID than DIT.
Yep. And comparable IS and recall. It also did better than some recent pixel-based models like Fractal MARH and was competitive or better than others like ADMU, City2, VDM++ Lay.
So operating directly in pixel space, it's really holding its own, even outperforming some latent models.
Absolutely. It really highlights the strength of their approach.
Very impressive. Okay, let's move on to text-to-image generation then. How do they tackle that?
They used a two-stage training process. First, they started with the model pre-trained on ImageNet at 256 by 256.
Okay, transfer learning.
Exactly. Then they trained it further on a big subset of the LAION dataset, still at 256 by 256.
Right.
And the final stage was fine-tuning on a curated high aesthetic dataset, this time at 512 by 512 resolution. All the text-to-image results they report are from this final 512 model.
And how did they measure how well it followed the text prompts?
They used 3 pretty tough benchmark datasets. T2I Comp Bench, which really tests binding attributes like getting the right color on the right object.
Tricky stuff.
Yeah. Then Geneval for broader composition like coherence and spatial layout, and DPG Bench for handling more complex descriptions.
A comprehensive evaluation.
For sure. They generated lots of images for each benchmark and used quantitative metrics to see how well the images matched the text.
And the quantitative results, how did PixelFlow do?
Table 5 shows it did really well across all 3 benchmarks. It was particularly strong on T2I Comp Bench, especially for getting colors and textures right.
Nice.
And it got solid scores on Geneval and DPG Bench too, beating several established models like SDV 1.5, DLE2, even SDXL on some metrics.
So competitive, even against the big names in text-to-image.
Definitely competitive. It really shows its potential for handling complex natural language prompts.
And they included visual examples too, right? What do those show?
Yeah, lots of visuals. Figure 3 actually shows the intermediate steps during sampling, so you can see the denoising happen across resolution.
Oh, cool. Like watching it come into focus.
Exactly. And then figures 5 and 6 have final images at 512 by 512 and even 124 by 1024. They look great high fidelity, good detail like fur or reflections.
And they match the prompts well.
Yeah, they seem to show really strong text-image alignment, even capturing fine-grained details from the prompts.
Okay, so really strong results overall, but no model is perfect. Did the authors mention any limitations?
They did, yeah. A couple of things. One is that even though the intermediate stages are efficient, that final generation stage still needs full resolution self-attention.
So the last step is still computationally heavy.
Right. They say it takes up about 80% of the inference time. So while it's more efficient overall, that last step is still a bottleneck.
Okay, fair enough. Anything else?
They also noted that training convergence tends to slow down as the sequence length gets longer.
Which happens with higher resolutions or smaller patch sizes.
Exactly. So those are areas for potential future work, improving that final stage efficiency and maybe speeding up convergence for very long sequences.
Makes sense. So let's bring it all home. What's the big takeaway here? What's the significance of PixelFlow?
I think the main thing is that PixelFlow is a really compelling proof of concept. It shows you can build a highly competitive end-to-end generative model that works directly in pixel space. By ditching the need for separate VAEs and upsamplers, it genuinely simplifies the whole generative pipeline.
Yeah, that seems like a big win.
And its strong performance, both class-conditional and text-to-image, sometimes hitting state-of-the-art levels, it just strongly suggests that direct pixel space generation is a really viable and exciting path forward for generative AI.
Absolutely. It feels like a really strong challenge to that dominant two-stage LDM approach.
It really does.
So as we wrap up this deep dive on PixelFlow, here's something to chew on. Given what we've seen with this direct pixel space approach, what does the future hold? Could we see even more tightly integrated, even more efficient generative models? And how might these kinds of direct generation approaches move beyond just images? Could they fundamentally change how we generate high-fidelity video or audio, or maybe even complex 3D scenes down the line?
That's the big question, isn't it? Definitely a fascinating space to watch.
It certainly is. Thanks, everyone, for joining us for this deep dive.